Today we are going to understand a very interesting fact that is called FAZANS rule. It's about the character of covalent bonding and the ionic bonding. FAZANS rule. Before we proceed with the rule, we have to understand one fact. And what is that? At what we are saying it, that it's a covalent character and ionic character of a bond. Why aren't we saying it's a covalent bond and an ionic bond? Because there is a fact that যখন আমরা বন্ডিং এর কথা বলছি and if we proceed through the wave nature of an atom and the electron density, then we see if there is a nucleus, there is the electron density surrounding this of a particular atom, let us say A, and there is another nucleus and its surrounding electron density of a particular atom, let us say B. Now, when they come closer, what happens actually? Because of the positive charge of nucleus, as there resides protons, they always attracts the electron density surrounding by this. So, this nucleus always will attract its own electron density surrounding by this nucleus, as well as the electron density surrounding by this nucleus when it comes close to this atom. That's why after coming closer, there will be a deformation in the electron density surrounding this nucleuses. How they will deform? As this nucleus exerts an attraction force on this one, we have learned it already earlier. So, this electron density will deform towards it a little bit, and this deformation we call polarization. This is the main key fact. As much as the polarization occurs, there is a high chance of being covalent in nature of that particular bonding. When we studied the covalent bonding in the earlier topic, then we learned that when it is covalent bonding, this deformity increases electron density in between these two nuclei, and that electron density is attracted by both of these nucleus, and they always get together to hold that electron density, and by that means the covalent bond is formed actually. And thus what we see here, as much as the deformation occurs, the covalent character increases. If there is no deformation, direct electron transfer, then the ionic character of bonding increases. So, FAZANS rule actually tells us how it depends, how the deformation plays the key role to determine the characterization of a bond, whether it is covalent character or it is ionic character primitively or predominantly. So, here we learn one new thing, that there is no bond which is 100% ionic or 100% covalent, because always there will be a chance of a less deformation. So, 100% ionic bond, it's not possible, and 100% covalent bond, that is also not possible, because to being a covalent in character, a bond to be a covalent in character, there needs a minimum, at least a minimum percentage of that much deformation to be predominant. Now, no bond is 100% ionic or 100% covalent. The second thing is what we learn, that is, as deformation or polarization increases, covalent character predominates. সো এখনো পর্যন্ত আমরা কি শিখলাম, যে কোনো বন্ডই 100% আয়নিক হতে পারে না, 100% সমযোজী হতে পারে না, এবং যত পোলারাইজেশন বা ডিফরমেশন বাড়বে তত ওই বন্ডের কোভ্যালেন্ট ক্যারেক্টার বাড়তে থাকবে। এবার এই কারণেই যেহেতু 100% আয়নিক বা 100% কোভ্যালেন্ট হতে পারে না, সেই কারণে কি না আমরা কোভ্যালেন্ট ক্যারেক্টারটা কীভাবে বাড়ছে সেটার উপর ডিপেন্ড করব কে আয়নিক কত। যত কোভ্যালেন্ট হবে ক্যারেক্টারটা বাড়বে তত হচ্ছে গিয়ে লেস আয়নিক, যত কোভ্যালেন্ট ক্যারেক্টার কমবে তত হচ্ছে গিয়ে মোর আয়নিক। এখন there are some factors which actually determines how the deformation increases. If we know those factors which determine how deformation increases, we can easily learn about a particular bond if it has covalent character in dominancy or ionic character in dominancy. That means much covalent character or less covalent character, or the reverse, less ionic character or much ionic character. So we need to know those facts only which determine the power of deformation, how it increases or it decreases. It's a simple thing. If from the very start we assume that both the atoms are ionic in character, we assume that both the atoms are ionic in character, whether it is ion or not, but we assume that they are ionic in character. So there must be a cation and an anion. Now, polarization power. If this cation has to polarize this anion in much aggressiveness, then what the nature it must have, or what the nature it must possess to deform this anion much better. If this anion has a very high charge density, that is, in place of A plus it will be like A2 plus or A3 plus, let us say An plus, then it will attract the electron density of B minus more and more, thus polarizing the anion more and more. So when the cation has a large charge density, polarization is high, thus covalent character increases. Same thing goes for the anion. If the anion has a very high charge density, then the electron surrounding the nucleus of the B atom will be held by its own nucleus very loosely. As a result, the electron density will be deformed very easily by the cation. So, this rule is also applicable for the anions as well. So, this we will write cation or anion. Any one of them, if has a large charge density, the polarization is high, thus covalent character increases. As for example, if we take the example of SnCl2 and SnCl4, in this case anions are the same, both are chloride anion, and the cations are Sn2 plus and Sn4 plus. Now, as Sn4 plus has high charge density, then it will deform the chloride ion very much more than it does in Sn2 plus state. That is why Sn4 plus is more covalent in nature than Sn2 plus. So, Sn2 plus is less covalent than Sn4 plus, or rather we say Sn2 plus is more ionic than Sn4 plus. Again, if we take an example of Ca F2, Ca Br2, Ca I2. When we go from F, Br, I, we see the size of the anion, it increases from fluorine to bromine to iodine. Thus, there is a chance of deformity higher in fluorine. There is a chance of high deformity in iodine than bromine than fluorine, as it is large in size. So, the electron density around the nucleus of itself becomes loosely held and they easily get deformed by the same cation. Now, the second part is the size of the cation. If size of the cation decreases, that means the nucleus has more proficiency to attract the surrounding electron density towards itself, thus more deforming the electron density of the anion towards itself. So, if the size of the cation decreases, then polarization increases. Thus, covalency increases. Simple. যত আমার ক্যাটায়নের সাইজ ছোট হবে তত কি হবে যে ক্যাটায়নটা বাইরের ইলেকট্রন ডেন্সিটিকে নিজের দিকে অ্যাট্রাক্ট করার ক্ষমতাটা বাড়বে, যত নিজের দিকে অ্যাট্রাক্ট করার ক্ষমতাটা বাড়বে তত দ্যাট মিনস অ্যানায়নের ইলেকট্রন ডেন্সিটিকে সে বেশি ডিফর্ম করতে পারছে টুয়ার্ডস ইটসেলফ। Thus, as there occurs an increase in polarization, the covalency character always increases. Now, the third one, as I said earlier, the size of anion. Large size of anion. Large size of anion, it means as the size of the anion increases, the electron density surrounding its nucleus will be loosely held, thus will be deformed easily by the cation, and thus the covalency character increases. The previous example was for actually this one, CaF2, CaBr2, CaI2. And about the charges, we can take another example, CaF2 and CaO. Which one is more covalent? When we say about O2 minus, then as the charge increases, the electron density around this nucleus will increase, and the electron density will be loosely held by this particular nucleus of oxygen atom. Thus, the electron density of O2 minus will easily be deformed by Ca2 plus than in CaF2. So, this will be more covalent in character in case of CaF2 and CaO, F minus, O2 minus. And here in the case of size of an ion, as we go from F to Br to I, we see that the ionic size of I minus is greater than Br minus is greater than F minus. Thus, the electron density surrounding the nucleus of iodine is more loosely held than Br than F. So, easily they are deformed by calcium as in the order of I minus greater than Br minus greater than F minus. Thus, the covalency character increases towards the larger anion. Covalency character increases. The last one is the pseudo Noble configuration. This was the pseudo Noble configuration. Pseudo Noble atom. And what is that? If we say any atom's electron distribution is like NS2 NP6, its noble gas atomic electronic distribution or configuration. And if we say like N-1 D10 NS2 NP6, then it is pseudo noble atom, because it has 18 more electrons before this NS2. It has 10 more electrons before NS2 NP6. Now, what will happen there? There is a term called shielding effect. As there is D involved, which causes lower shielding effect, then this atom will be tightly bound to the nucleus of this atom. Thus, it will exert more deformation on the anion, and that is why, for example, in case of NaCl and CuCl, for NaCl there we see Na plus, that is 1s2 2s2 2p6, and for Cu plus, that is 3s2 3p6 3d10. 4s1 was the electron for Cu which has been eliminated when it converts itself from Cu to Cu plus. Now, as we said, both the ion has nearly the same radius, but it has low shielding effect, and thus the electrons of this 3s2 and 3p6 will be tightly bound to the nucleus more than Na plus. Thus, Cu plus will exert greater polarization on Cl minus and Na plus will less. Thus, the covalent character of CuCl is more than NaCl, and ratherly we can say that NaCl is more ionic than CuCl. As for the lower shielding effect of d orbitals, this is very important. And as per these 4 discussions or 4-point rules, we can easily compare any compounds who have the more covalent characters or more ionic characters on basis of these rules by periodic properties, ionic radius and the cationic ionic radius and the ion charge density. These were all the FAZANS rule, very impressive. Like if we sort it out, we can say like in case of cation, in case of anion, here we table it, make a table like charge, size. When the charge is high in both cases, any one of them, then character, percentage character, higher percentage character will be covalent. If the size of the cation is larger or the anion is larger, then covalent. If it's smaller or this smaller, then it's ionic. Same here, if low or this is low, is ionic. And the last but not the least and very interesting fact was pseudo noble configuration of cation. That will be more covalent if there exists such character. This is the table by which we can draw the FAZANS rule at a glance, and by FAZANS rule we can easily compare any compound about their covalency or ionic nature, which one will predominate or not. So, this is. Thank you.